Aviv Hassid, and I'm a PhD student under Chaim Cohen, and this is our presentation regarding call analysis through a combined TGA DSC analysis. Well, first of all, what is exactly coal? Coal is actually plants that were buried under rocks and dirt, and through the ages, the heat and the pressure transform into what we know today as coal. The coal formation actually separate into two stages. The first one is the biochemical stage, where the flora decompose into peat. In the second stage, the geochemical, the peat goes through carbonization into lignite, bituminous, and anthracite coal. During this stage, there is an emission of water, CO2, CO, and other volatile hydrocarbon and organic matters. Also during this stage, there is, of course, an increase in the carbon percent, as well as the calorific value, while the percent of the hydrogen, oxygen, nitrogen, and sulfur decrease. Now, when we talk about coal analysis, we mainly mean for four different properties. The first one is the moisture, the amount of water that are in the coal. The less the water, the better the coal rank is. The second is the volatile matter, which is the gases emitted during the pyrolysis process. It helps determine the coal rank and the combustion process profile. Next is the ash, which is the inorganic residue remain after the combustion process. And then we have the calorific value, which is the energy produced during combustion. Now, we divided the coal into mainly four types of coal. The lignite, the subbituminous, bituminous, and anthracite. They mainly differ from each other by the carbon percent and the calorific value, where the lignite got the least of both and the anthracite got the most. But they also differ from one another, as for the lignite contain high percent of aliphatic groups and high moisture content, where the bituminous coal contain higher aromatic content and low moisture, and the anthracite contain only aromatic carbons and close to no moisture. But what are the problems we are facing today with handling and analyzing the coal? Why are we here? Well, the first problem is analytical problem. The present used today are slow and expensive. And the second problem is a storage problem. If a heat emission during the low temperature oxidation is higher than a heat dissipation, a self-heating of the coal may occur, which may lead to a hotspot, creating of a hotspot, and a self-ignition. This may lead to a decreasing in calorific value, release of toxic and flammable gases, and the increase of the operational cost of handling the coal. I mentioned earlier the coal analysis method, but what are the present methods used today? Well, first of all, for moisture, we dry the coal under air or nitrogen atmosphere for 1 hour at 100 to 130 degrees. The mass loss equal to the to the content of the moisture, to percent of the moisture. For volatile, we heat the coal for 7 hours at 900 to 950 degrees in an under inert atmosphere. And again, the percent of mass we lose during this process is the percent of volatile gas released during it. For ash, we heat or burn the coal under 800 degrees for 1 hour, or alternatively go through two-stage heating procedure. And the percent of mass remain is what we called ash. And as for calorific value, we insert the coal into the Abom calorimeter and measure the heat released during the process. For coal, our coal research goals are first using the thermal analysis evaluation of coal properties, using the thermal analysis for evaluation of coal properties. And second, we determine the combustion pattern, the chemical reaction of lignite and bituminous coal through thermal analysis. Now, the coals we studied are the bituminous Bailey coal, fresh and weathered, treated, and the lignite Hambach coal, fresh and treated, each one used in Israel and Germany respectively. And each coal will be studied under 3 types of atmospheres: oxygen, air, and nitrogen. The main tool we use is the thermal and gravimetric analysis, TGA, and the DSC differential scanning calorimeter. What is that device? Well, the thermogravimetric analyzer is a device in which the chemical or the physical properties of the sample is measured through the mass change versus the temperature. While in the different scanning calorimeter, we measure those properties through the heat release versus the temperature. The main advantage of this device is using that device enables us to measure the coal properties much faster and more efficient than the other methods. Now, our procedure is quite simple. We take a sample of the coal, insert it into the TGA DSC under 3 different gases. We run the device, the TGA DSC, run between 30 degrees to 100 degrees Celsius at a 10 degrees per minute heating rate. And we analyze the result. And here are the equation we use for the analysis of the result, quite similar to what we mentioned earlier about what each of those properties represent. Here are some of example for a result. In this slide, we see a graph of the Bailey BA, the bituminous Bailey under air atmosphere. In the upper graph, treated particle size between 74 micron and 250 micron. In the middle, between 250 to 350 micron, and at the lowest, particle size of above 350 microns. The green line you see represent the TGA, while the blue line represents the DSC. Now, as you can see, between 0 and between 30 degrees and 130 degrees, there is a mass loss during the for loss of the moisture. Then we go through a combustion process in which the major mass loss is occur. And finally, after 800 degrees, or in this case, between 600 and 700 degrees, we come to pretty much stable graph of the TGA, which represent the ash remain after this process. Had we done that in inert atmosphere, the mass change we see between 130 degrees to 950 degrees we see on the right will help us determine the volatile matter content. Additionally, we can see in the green line, the green graph, the DSC, that we can determine the aliphatic site oxidation and aromatic site oxidation. In this case, we can see there is a much higher aromatic site oxidation, which correlate with what we said earlier about that in the bituminous coal, there is a higher aromatic content. Now, with the Hambach like that example for result, we can see that first of all there is a much higher mass loss of the treated Hambach coal. Additionally, we can see that in the blue graph of the DSC, there is actually two aliphatic site oxidation, which represent two different group of aliphatic groups. Furthermore, we can see that because the TGA is less precise, less sensitive device than the DSC, that previously we haven't seen the difference between the aliphatic and aromatic content. But here, according to the green state between 400 and 600 degrees, we can see that even in the TGA, we can differ between the aromatic and the aliphatic side. And again, as we said earlier, in the lignite coals, there is a higher content of aliphatic groups. To summarize our result, we present here this table where in the black we can see the result we got from the TGA, and in the red the result we got from the classical DIN analysis, which is the classical method used to analyze coal in Germany. The right column represents the type of the coal. For example, BA350X represent Bailey coal, bituminous Bailey coal, with particle size above 350 micron. As we can see here, there is a really good correlation between the TGA result and the DIN result, which prove our presumption earlier that the TGA can replace efficiently, it's much faster, the classical method used up to now. Now, as for the DSC result, it's a different story, because the result we got from here are significantly lower than the result we got from using the bomb calorimeter in the lab, in which you can. Now, we presume that in order to improve this correlation, we need to improve our analysis of the DSC. For example, we need to improve the calibration of the DSC for each gas separately. Now, conclusion at this point are to follow. First, we successfully characterize the TGA properties of moisture, ash, and volatile matter. So a very good fit between the TGA method we present here and the classical bin or American ASTM for measuring coal. So that the TGA can perform the coal analysis much faster. What took before like half a day or a full day can take like 3 hours in the classical method. In the method we present here today, and much more efficient than the classical method, which means much more safer since we don't have to wait too long to have the coal wait too long in the storage. For moisture, after much testing, we conclude that the air environment is the best. Now, additionally, the combined TGA DSC can characterize the aromatic and aliphatic site of the coal, and the two aliphatic groups of the coal and the two aliphatic and aromatic groups during the combustion process, which could help the engineers of the engineering the power plant to work to operate much more efficiently and save both money and time. Now, the determination, as we said earlier, of the calorific value via the DSC need to be improved. And that, as we mentioned earlier, probably with better calibration of the gases, we can improve the correlation between the DSC and the classical method used up to now. And that's the end of my result. If there are any question, please ask.